MGF 1107, Chapter 3, Section 2. Before I start explaining some example problems, you need to understand some definitions. First definition is an Euler path. It's a path that passes through each edge exactly one time. Then you have an Euler circuit, which is a path that passes through each edge exactly one time, but starts and ends at the same vertex. Remember, definition from section 1. A path doesn't necessarily have to start at the same vertex and end at the same vertex. A circuit starts at the same vertex and ends at the same vertex. Odd vertex has an odd number of edges connecting to the vertex. So it's going to have an odd number of lines connected to it. Even vertex. It's going to have an even number of edges connected to the vertex, even number of lines. This is going to become important when we look at Euler's theorem. If a graph has an Euler path, then the graph is traversable. Traversable means that once I put my pencil down, I can trace the whole path without raising my pencil. All right, let's look at some of these examples. All right, first of all, in order to even be considered an Euler path or an Euler circuit, the graphs must be connected. That means there can't be a vertices out in space somewhere or a line. In this particular example here, we have two edges to A, so it's an even vertices. B has four edges to it, so it's even. D has two, even. E has four, even. C has four, even. F has four, even. There are no odd vertices in this graph. So if we look at Euler's theorem, it says a graph with no odd vertices will have at least one Euler path, which is also an Euler circuit. An Euler circuit can be started in one vertex, and it will end in the same vertex. So letter A here satisfies part 1 of Euler's theorem, no odd vertices, so it definitely has an Euler circuit and an Euler path. We come to the second one. A has two edges, even. B has two edges, even. F has two edges, even. E has two edges, even. C has three, odd. D has two, odd. Exactly two odd edges. Second rule in Euler's theorem, a graph with exactly two odd vertices has at least one Euler path, but no Euler circuits. Each Euler path must begin at one of the two odd vertices, and it will end at the other odd vertex. Very important. So if you were tracing a path for this one, you would have to start at either C or D, and it would end at the other odd vertices. So let's just look at the two rules again. No odd vertices has an Euler circuit and an Euler path. Exactly two odd vertices has only an Euler path, and you must start at one of the odd vertices and finish at the other one. Third example. Three edges at A, odd. Four edges at B, odd. Three edges at B, odd. Three edges at E, odd. Three edges at D, odd. Four edges at C. See how we have more than two odd vertices. Rule 3 says a graph with more than two odd vertices has neither an Euler path or an Euler circuit. That's your three rules of Euler's theorem. Let's look at two examples. All right, this is example 3 on page 805 from 13.1. This is a diagram of a gym. And we have training room here, locker room, training room, locker room, training room, and then the weight room here. So what they did was label these they labeled the outside, which is out here, with a vertices O. It then is drawn a line to locker room A. You have Ray's training room, Sierra's training room. You have the health and weight center, which is in the middle. And then down below it, you have locker room B, and then you have Keegan's training room and Chet's training room. Remember, in order to be considered having an Euler path or Euler circuit, everything must be connected. So what they did was they put the vertices up here first, and then they connected it. So if we look at this diagram of the gym, see how O has odd vertices, it has 3. See how R has 2, S has 2, A has 3. H has 6, 2, 2, 2. So we have exactly 2 odd vertices, which means that's rule 2 for Euler's theorem, which means it has an Euler path. So remember, we got to start at one of the odd vertices by rule 2. So we're going to start at O. Once we start at O, the dashed lines show our path. We're coming from O to all the way down here to H. And from H, we're going all the way down to K. From K, we're going to B, then B to C, then C back to H, then H to R, R to A. Then from A, we're going to S, S down to H, and then from H, we're going around here, back to O. And we've completed our Euler path. Let's look at a second example. Here's the diagram here. This is what we call the Crime Stoppers problem. This was also in 13.1. Here's the original diagram here, talking about the streets. See how we have on street here, these are streets, these are streets, these are streets. Okay? So the first thing I want to look at here is, again, I want to count odd and even. So A is even, E is even, H is even, I is even, B is even, F is even, C is even, J is even, G is even, D is even, K is even. So in terms of this one, we have no odd vertices, so this satisfies rule 1 of Euler's theorem. So we have an Euler path and an Euler circuit. So based on the problem from 13.1, we're going to start at A. And we'll move to B. And then from B, I'm moving to C, C to D, D to K, K to J, J to I to H, H to E. Then I'm going back up to B, down to F. From F, I'm going to C, C, I'm going to G. Then at G, we're circling around, coming down to J, J to F, F to I to E, then back to A. Because remember, an Euler circuit, if you defined it as an Euler circuit, meaning it doesn't have any odd vertices, it must finish at the same vertices that it started at.